Welcome back to TechTide Digital Lifestyle, your trusted source for professional marine engineering tutorials. In this Part 3 lecture, we will focus on the autopilot system and steering control modes, one of the most critical components for modern ship navigation. Understanding autopilot integration with the hydraulic steering gear is essential for safe and efficient ship operations. By the end of this lecture, you will clearly understand how the autopilot system operates, the different steering modes, and how course corrections are made automatically. This knowledge is also very important for competency exams and onboard practice. So subscribe this TechTide Digital Lifestyle and like, comment and share this video. Recap of previous lectures. Before we dive into autopilot, let's quickly recap what we've covered so far. In Part 1, we explored rudder types, forces acting on the rudder, and basic steering gear arrangements. In Part 2, we examined the hydraulic steering system, from the hydraulic power unit to pumps, actuators, ram and rotary vane types, control systems, and safety arrangements. Having this foundation will help you better understand autopilot operation because autopilot essentially controls the same hydraulic steering gear automatically. Remember, autopilot does not replace manual knowledge, it builds on the fundamentals you already learned. Introduction to autopilot. An autopilot system is designed to maintain a ship's course automatically, reducing the need for continuous manual input. It increases navigational accuracy, reduces crew fatigue, and improves fuel efficiency. Autopilot systems are not just about convenience, they are essential for long voyages and precise maneuvering in busy shipping lanes. Key components include the autopilot controller, gyro or heading sensor, rudder follow-up mechanism, and integration with the hydraulic system. Understanding how these components communicate and respond to heading data is critical for every marine engineer and deck officer. Steering modes overview. Autopilot systems operate in several steering modes, each with specific applications. 1. Hand steering, manual, operator fully controls the rudder. 2. Non-follow-up, NFU, rudder movement without feedback, operator monitors rudder manually. 3. Follow-up, FU, helm commands are automatically followed by rudder movement. 4. Auto mode, autopilot automatically sends rudder commands based on heading input from gyro or GPS. Each mode is important for redundancy and ensures safe operations during system failures or emergencies. Understanding these modes helps operators switch seamlessly between manual and automatic control. Gyro compass integration. The gyro compass provides real-time heading information to the autopilot system. The autopilot controller uses this data to calculate rudder corrections and maintain the desired course. Accurate heading data is essential, even a small error can cause deviation over long distances. Integration with the steering gear ensures smooth automatic control. This also allows autopilot to correct for environmental forces such as wind, currents, and waves, maintaining the ship on a steady path without constant human input. Autopilot controller components. The autopilot controller is the central processing unit of the entire steering automation system. It continuously receives heading data from the gyro compass and compares it with the desired set course entered by the operator. The difference between these two values is called the error signal. This error signal is processed by the PID controller, proportional, integral, and derivative control logic. The proportional part reacts to present error, the integral part corrects accumulated past errors, and the derivative part predicts future trends based on the rate of change. Together, these three controls ensure smooth, stable rudder movement without oscillation. In your slide diagram, you can see the input arrows entering the PID block and output arrows moving toward the hydraulic actuator. A properly tuned PID system reduces fuel consumption, prevents zigzag steering, and ensures course stability even in heavy sea conditions. This is why calibration and tuning of autopilot parameters are extremely important on board. Rudder follow-up mechanism. The rudder follow-up mechanism ensures that the actual rudder position matches the commanded angle precisely. As shown in the 3D cutaway diagram, the feedback sensor mounted on the rudder stalk continuously measures the rudder angle. When the autopilot or helm sends a command, the hydraulic actuator moves the rudder. At the same time, the feedback signal compares the actual position with the desired position. If there is any difference, the system continues adjusting until both values match. This closed-loop feedback prevents overshooting, oscillation, and unstable steering behavior. Without follow-up control, the rudder could move excessively, causing zigzag motion or even structural stress. In rough weather, this mechanism becomes even more important because wave forces constantly try to disturb the rudder position. The follow-up system ensures stability and precision at all times. Types of autopilot systems. Autopilot systems differ depending on vessel size, trade route, and operational requirements. The basic autopilot maintains heading using a simple PID loop and is suitable for smaller vessels or short voyages. Advanced systems, often integrated into an integrated bridge system, combine gyro compass data, GPS position data, and route planning software. These systems can automatically follow a predefined voyage plan, adjusting course based on waypoints. Yaw and course stabilization systems are designed for larger vessels operating in rough seas. These systems detect rolling and yawing motion and make predictive rudder adjustments to maintain stability. In your slide, the 3-panel layout visually shows this evolution from basic to advanced systems. Understanding these types helps officers select the correct operational mode for safe navigation. Safety or redundancy. Safety is the highest priority in steering systems. Autopilot must never compromise manual control authority. That is why manual override is always available. If the autopilot detects abnormal heading deviation, sensor failure, or power interruption, it triggers alarms and can automatically disengage. The steering control immediately reverts to manual mode. Modern ships often have dual gyro systems, dual control units, and even dual hydraulic pumps for redundancy. This ensures continuous steering capability even if one component fails. In your slide visual, you can see highlighted redundant sensors and emergency override mechanisms. This redundancy is also required under international maritime regulations to ensure safe vessel operation under all conditions. Practical autopilot operation. Operating autopilot may look simple, but professional supervision is always required. First, the officer sets the desired heading on the control panel. After verifying gyro accuracy, autopilot is engaged in auto mode. The system begins calculating corrections automatically. However, the officer must monitor rudder angle indicators, heading display, and environmental conditions. Sudden wind shifts or traffic situations may require immediate manual takeover. Good seamanship requires understanding when to rely on automation and when to intervene. Autopilot assists navigation, but it never replaces human responsibility. Your step-by-step diagram on the slide clearly shows this operational sequence, from setting course to monitoring and being prepared for manual control. As we come to the end of this lecture, let's quickly summarize what we have learned today about the autopilot system and steering control modes. In this session, we understood how the autopilot system integrates with the hydraulic steering gear to maintain a ship's course automatically and accurately. We discussed the role of the gyro compass in providing real-time heading data and how that information is processed by the autopilot controller. We explored the PID control logic, proportional, integral, and derivative actions, and how this intelligent control system calculates precise rudder corrections to prevent overshooting and oscillation. We also learned about the importance of the rudder follow-up mechanism, which ensures that the actual rudder angle matches the commanded angle through a closed-loop feedback system. We examined different steering modes, including hand steering, non-follow-up, follow-up, and auto mode, and understood when each mode should be used during ship operations. In addition, we covered the different types of autopilot systems, from basic heading control to advanced integrated bridge systems with GPS and route tracking. Most importantly, we discussed safety and redundancy, manual override systems, alarms, dual sensors, and the critical requirement that autopilot must never replace human supervision. Automation supports navigation, but responsibility always remains with the officer on watch. This knowledge is extremely important for marine engineers, deck officers, and ETOS, both for onboard operations and for competency examinations. Understanding how autopilot interacts with hydraulic steering gear is essential for safe and efficient vessel control. If you found this lecture valuable, please support the channel by liking this video, sharing it with your colleagues, and leaving a comment below about what topic you would like to see next. Don't forget to subscribe to TechTide Digital Lifestyle and turn on notifications so you never miss upcoming marine engineering tutorials. Also, make sure to visit our channel playlist, where you'll find the complete steering gear tutorial series along with other important marine system tutorials designed specifically for professional seafarers. Thank you for watching, stay safe at sea, and I'll see you in the next lecture where we will continue building your technical knowledge step by step.